Um, so yeah, first, I guess if anyone wasn't here last week and like to introduce themselves and talk about what they'd like to get out of this session or this group, I want to open it up now for you to be able to do that.
Hi, this is Deanna. My background is I have a degree in computer science, 20 years of software engineering, and have become more involved with RChain. I'm really interested in learning a little bit more about the foundational calculus that's behind the rolling language so that I better understand that.
Awesome. Good morning, Deanna. Thanks for joining us. Okay, so I thought we would start off this morning by doing a quick overview of sort of the grammar from last week and then have some examples in the JSON-Py interpreter. So Glenn offered to do that. So Glenn, take it away.
Okay, great, thank you. I am going to share my screen here. So everybody, did people see my screen? Yeah. Okay.
Yeah, got it.
Yeah.
Okay, so I'm starting with one of the first examples in Milner's text. And it's a real simple example. It's been translated a little bit in syntax to fit what works in the JSON-Py interpreter. Just that the only real change, there's two changes to pay attention to. One is that this is the syntax for sending on the name X. So these angle brackets replace what in Milner's text is a bar over the letter. So when it's an angle bracket on each side, it's an output on the name that precedes it, and then the parentheses mean it's a receive on the name that precedes it. And then the other thing that's different is that instead of a 0, I use a semicolon to indicate the process that's the inactive process. But otherwise, it's the same. So I thought we'd just run through this example, kind of step by step of how it would evaluate. And the first, so that's the example. And then over here, in order to evaluate, it's helpful to have this table set up. And I'll get to this. Well, first, I'll explain them. So one is the context. We'll get to what that means. The prefix and a continuation. I think examples will just describe that, how that works. So let me go back over here. If we remember, this bar means that it separates processes. So here we have three processes. This is one of them. This is two of them. This is the second one, and this is the third one. So to make that easier, I think what I'll do is I'll put these on separate lines. And so these are all running concurrently, these three processes, and they all start with their first prefix. So what's on the left, in a normal language, we would have an instruction pointer. In PyCalculus, we have three of them, and they start here. There's the first prefix on the left. Any one of these we could execute first, but let's just start top to bottom. The way it works is we look here and we see the name X. We go over to our table, and we don't see any data here. So what we would be looking for is a match for some process that's waiting to receive on X because we're sending on X, and there isn't anything. So what we do is we copy that over. I'm going to put 1 here as a placeholder. I'll call this context 1. And our prefix is this, and our continuation is this. So the continuation is the process that follows the prefix here that's currently guarded or is waiting for some other process to be ready to receive what's being sent here. Okay, so this process is now halted. We can go down to the next one, and we see that we're receiving on X. And now when we go to our table, well, that's what we just put there. So what we can do is we have two things to do once we find a match. We take the continuation and we put that in the place of its previous context. So just keep that in mind for a second. And then here, we take this Y that was sent, and let's do that. We'll make that notation that U is going to get replaced with Y. Now we can pull this out of the table. That's gone. Let's finish this guy here. What this means is that where there is a U in its continuation, we're going to replace it with Y. So that's pretty easy. Place that with Y. And we're done. And so now we're back to this is how this process is now reduced by the rules. And we're left with this guy. Again, we have processes that could go in any order, and so we could continue with this if we wanted. Create a 1. So on, and then here we would send on the same thing. For some reason, I feel like this isn't working out the way the example wanted it to, but maybe I'm wrong.
Nope, this is correct.
Okay.
Yep, I think it's the example is supposed to say, right, that there's two ways that this can reduce.
Yeah.
Either the line 4 could sort of combine with the line 6, or the line 8 could combine with the line 6, but they don't both combine.
Yeah. So that's what we wind up with as this evaluates. This top process went to its nothing process, meaning it's complete, and these two processes wound up waiting in memory, or in our chain's case, this would be called R space. This is the tuple store over here, this table. So I hope that helps. That's kind of a line by line how it executes. If we went back, if we would have executed this from the bottom up, let's say, then rather than Y coming in here and replacing U, it would have been Z that replaced U, and this would have become Z. And that's the example he's trying to get at. And there's the language doesn't define. It's could be either are possible reductions or executions of this code.
So in reality, it's whoever gets there first, essentially. Is that how it works?
Yeah.
So in reality,
it seems like there's two completely different outputs.
So it's not guaranteed that whoever gets there first is going to get the meet, the collect. Race conditions are not fair.
Right.
In our chain, validators get to decide them, and maybe even a single validator gets to decide them. So yeah, there's no notion of fairness in races, in first come, first serve.
Okay.
And if we execute this let me run it in the JSON Pi. So if we run this in, can you see? Yeah. If we run this in JSON Pi, actually I'll go through it in steps. What we'll find is here in the JSON Pi, it is deterministic because I run effectively the right-hand side of two parallel processes. the way this gets parsed is two sets of parallel processes, like in a tree. So here, the X send Z will run first, which then matches with this input where Z is replaced, and we continue through, and we wind up with our two prefixes in this continuation. Same results. Okay. Just do two more examples. One has let's see if I can, that doesn't really help. I wanted to clear the space. Okay. Okay, so this has a restriction. We briefly talked about that. What we're doing here when we create this X is it's saying that if there's ever an X, well, intuitively it says that if there's ever an X before or in any other process, we don't mean that X. It's in the reality of writing a program, we can only use so many letters, and we don't know if some other process has chosen those same ones. And so there's this restriction that says, I mean a completely new identifier X. Don't confuse it with any other X that's happened before. The way I implement that with JSON-Pi, you'll see here I put a tilde 1, tilde 2, so on and so forth at the end of them, that the tilde is not a valid character in the language, so you couldn't have created that that name.
Glenn, is this the same thing that, like, Mike Stay, for example, was referring to as an unforgeable name?
Yeah, exactly. That's right. And when you imagine these in a much broader system, even the well-known names, or I forget his terms, the anointed names, or I forget the right words, but
the blessed contracts.
Blessed, yeah. So in a sense, I think those will be nude, but they'll be nude up by some other process that we don't have access to. So it makes them available from a higher level, but they're absolutely unique from any other context. Does that make sense? Okay, so what this example is showing,
this looks like the same example as before, except the X is contained in the new X is contained in the sort of the first two processes there. So it's just I think claiming that, so everything in between the parentheses in front, that X is different than the X that's outside of that.
Yeah. So we should not see that this X here and this X here would match. Only this. So we should see Y come in for U, if I understand this correctly. So again, we're going to run this the right-hand side. It's going to put that in the table. Here you'll see where I have the tilde 1. That's how this X was internally renamed to make sure it's different from the other X's. And we'll step through and list out. And so yeah, the Y is what went from here over to this U, which replaced that. Okay. Next example. Okay, we briefly went over replication last time. There's no looping constructs so far in what we've studied, but this isn't really a looping construct, but it says keep running the process inside of here forever. And so if you can see, what it's doing here is it's listening on X, and here's a process that's sending on X and sending on X as well. But what should happen is we should see that on the first instance of running this process, it'll receive either one of these sends, and on the next time through, it should receive the other one.
So also, I think it's important to note that it isn't really a first and a next. The bang operator means that you have infinitely many of these things available running in parallel at the same time.
Yep, that's right. In the reality of how this gets implemented, it leaves just one waiting, listening on X here, and then as soon as that one is satisfied, it produces another one right away. We'll see that the reduction rules say that it reduces to yet another replicated process. We'll see how that happens. So we'll match first this first send. We got the Z first. We're finishing this. Okay, this time through we don't have a matching send yet because we haven't executed this. This time we get the Y, and we wind up with the send.
And we wind up with some extra stuff because it wasn't cleared, right?
Yeah, that's what's right. That's what winds up being pending after all that. Okay. One thing that came up in a meetup earlier this week is sort of like why such a complicated, or what seemingly complicated model of computation. And for me, one thing that I don't know that this will clear it up completely, but we use X's and Y's for just because it's easy to type and it's purely abstract anyway, so we just use X's and Y's. But we could think of this as like some website that's receiving, let's say, a search. Okay, so it's listening on a channel or a name, and when we call it a URL, I think that helps understand. Oh, I see. Okay, gives it a little more context. And what it's waiting for is, let's say, a search string, something like that. And here, when we type into our browser, we know the name. We either got it from a search engine or got it from DNS. It's that way, or we're just aware of it somehow. And so we can send on that channel, and we might look for, I don't know, something like that. Just to kind of give it's one way to help me understand why we would have this model when we think of our chain as being one kind of global computer. Then we would need to model everything that happens on the internet today, which is sending and receiving across URLs. So we can model that here in the PyCalculus. Kind of answers why, to me that answers why the seemingly more complex model.
Yeah, it's a nice example. Helps you see where the rubber hits the road.
Okay, so all right, Jake, those are the examples that we.
All right, awesome. Yeah, thanks so much. If you could quit your screen share so I could share mine. Thanks. All right, are you seeing my screen?
Yeah.
Yep.
Great. Okay. Let me try to get rid of some boxes here. Are there any weird shadows or anything? All right, so for defining programming languages, we need three things. We need grammar, we need equivalences, we need reductions. So last week, we went over the grammar, and we sort of kind of gone over hand-wavy explanations for the equivalences and reductions, but we haven't really given these formally yet. So I'm hoping to do that today. So the first thing is the grammar. It's what we went over last week. It allows us to answer, is this a valid program? When we were talking about sort of normal processes and non-normal processes, this was the grammar. And then there's the equivalences that we'll need. So this corrects for, this is how we correct for sort of fine-grained nature of our grammar constructions. So when we say, even out loud in English, run P concurrently with Q, P in that sentence comes before Q. And we want that to mean the same thing as run Q concurrently with P. So we need some way to say that, okay, these two sentences are equivalent. You can sort of swap back and forth between them, and you're not changing the meaning of your program. And then there's the reductions. So we need to define the actual steps of computation in our language. So when we say, x bar y pairs up with an xz, we want to say this is a communication that can happen. It's an output and input that are meeting. And when that happens, you reduce to another sort of form of your program, and you can't really do that step in reverse. So let's go over some necessary definitions that we'll need for sort of the equivalences. And so the first is free and bound names. Bound names are names which are under a closure, and free names are names which are not under a closure or could be bound by a process prefix. So essentially, you can think of them as like free variables. Free names are free variables that could change in your program by receiving another input before you've moved on. And we'll do some concrete examples because I know that can be pretty abstract. So in X, input some name and call it that name Y. This is an input. Your free name is going to be X because if you prefix something that inputted on X, that X name would change. But Y in the process after this is bound because no matter what you prefix with Y, once you hit this point in the program and Y is received from X, whatever you received from X is going to be what is bound to Y. What questions do you have about this example?
I don't have any questions about this example, but Jake, could you go back over what closure means briefly?
Yeah, so so this is a term that sort of I guess there's some technical definitions, and I don't have the full one at hand, but you can think of it as if you have a private variable in a class, right? That's closed. Or if you have a if you have a variable which can't be redefined sort of outside of the scope, the current scope that you're looking at, then it's under closure.
Okay.
Does that help?
Yeah, that makes sense.
Okay.
Thanks.
So then here's an output on X. You're outputting the name Y. So in this, you could prefix this process with something that could change X or Y. So X and Y are both free, and there are no bound names. And then there's this. We have the process.
I've got a question about the last one, Jake.
Yeah, sure.
Okay. So when you're talking about prefixing this, if that means basically if on the left side of this, if I add y parentheses a dot and then the x bar y, that would be the kind of prefixing you're talking about?
Yeah, exactly. Mm-hmm. The atomic prefixes.
Okay.
The construction that we talked about last week.
Got it.
Okay, so here's another one. So here we declare a new name X and a new name Y, and then we have a send on X and Y. Remember, in the process above, both X and Y were free, and now we're newing the names in front of it. So does anyone have a guess as to what the free and bound names would be?
my thought is if we prefix this with something, we're going to definitely be talking about different X's and Y's because these ones are new here.
Yep. So that's right. So both X and Y are bound names, and there are no free names in that process. Okay, here's a bigger process. And I want to use this to illustrate a couple of things. The first thing, can you see me highlighting here?
Yeah.
Yeah.
Okay. So the first thing that I want us to notice about this process, this isn't really related to free and bound names, but that these parentheses are unnecessary. And that is because, so right, those parentheses are sort of getting at what the scope of this new X is. And so if we remember our definition of normal and not normal process, we would see that that if this new X only applied to this part of the process, this part of the equation, this would create a non-normal process, and this over here would be a normal process, and we wouldn't really be able to add the two together. So I remove these parentheses in the next slide. But anyways, this might be a bit scary to look at. But I think if we break it down chunk by chunk, it's kind of easy to see what the free and bound names are. So let's just start with the right-hand side, since the left-hand side is scarier, in my opinion. So we have this process right here. We have new name Y. Okay, so we know that in this process here, Y is at least bound. So if it's bound over here, it will be a bound name. If it doesn't exist over here, it will be a bound name. But if it does exist as a free name over here, then this whole process would have the free name Y. And then we have X, which is a free name. We have A, which is a bound name. And then we have this dot P, this continuation of P. So this would mean that this overall process would have any other free name that's in P that isn't already bound by the sort of upper levels of this process. So so any free name in P that isn't A or isn't Y would become a free name in this process. And then any bound name that's in P would become bound if it's not free up here or free up here. All right. What questions do you have about this right-hand side? All right. So then over here, we have X being a bound name. But we remember that X over here is a free name. So even though X is sort of bound in the context of this process, X is still a free name overall in terms of this process. And then we have A, which is a bound name. And it's bound within this whole context. And then we have X, which is another it's bound within this context because it's nude over here. And then last we have this output on B, A. So this A isn't prefixed with this input. So this, what would have been a bound name A, is now free in this whole process construction. And then B is also free. So if you add that all up, what you get is that there are no bound names in this overall process construction except for any bound names that are in P that aren't referenced in the rest of this process. What questions do you have about that example? Was that understandable? There's kind of a lot there.
Yeah, I think you're doing a good job presenting it. I get this way more than I did when I just read the section.
Cool. All right, so now we can move on to defining our equivalences. there's this scary term, which I didn't know what it meant at first, which is talking about a symmetric monoid. But essentially, all this means is that this plus process summation component sort of acts like normal addition. So if you add a normal process, an empty process to the normal process, you receive the same normal process. If you add two normal processes together, it's the same as adding them in reverse. And you can group them in different ways, and you still get the same result. That's all that means. Is that these are all sort of ways of writing similar things. And then so we have the same thing in terms of processes and the run concurrently bar instead of the plus. It's the same construction. Anyone have a question, or what questions do you have about these two equivalences? Is there?
The p/lines notation, what does that mean?
Oh yeah, so this means that like the symmetric monoid is sort of defining like this congruence relation, this equivalence relationship. So okay. That's what's allowing you to put this here. So it's not saying that the processes are exactly the same. It's saying that the processes have this relationship when they're in this monoid.
Okay, got it.
Yeah, because there's you can think of weaker forms of equivalences as well, which we'll get into maybe in following weeks. This is sort of the strongest equivalence. This is structural equivalence, but there's other sorts of equivalences in processes. Okay, another one is that bang P is equivalent to P running in parallel with bang P, because bang P is supposed to signify infinitely many recurring Ps. So if you add another one onto it, you shouldn't change the meaning of your program. Another one is if you have a new name and then the empty process, that's just the same as the empty process. And another one is you can switch around these new names. So new name X, new name Y, P is the same as new name Y, new name X, P. Okay, the last one is that if we have this process P par Q, both P and Q running in parallel, and we have this restriction on X inside of this whole process. And if X doesn't occur as a free name in P, then it doesn't really matter that we have that restriction, because there's nothing that X could bind to in P. So that's equivalent to pushing this restriction just inside of just to apply to Q and not to P.
And if there's no X in Q, it would be equivalent to P bar par Q?
Yeah.
Okay.
Yep. What questions do you have about all of the equivalences?
I don't have any. It's pretty straightforward on that one.
Great.
Thanks for the mental break.
Okay, so then we have the reductions. So there's only one reduction in the pi calculus, and there's a couple of different restrictions on where they apply, but this is essentially the only rule. This is the communication or comm rule, and this says if we have an output matching with an input, and both of those processes have continuations, after the output meets the input, the output side will just reduce to its continuation, and the input side will also be replaced with its continuation, except whatever name we received. So in this case, we received Z here. replaces y in the process. So that's what this curly brace is. This means that whatever was written as y in this process is now replaced with z. Okay.
And if there was a z in P, you need to make it a different z, I believe. Is that right?
Yes. Yeah, that's true. That's true.
Well, isn't there some way that we can have those be the same z? I mean, what if that's our intention for those, that z that we're passing in to be the same z that already existed there?
So then we would be using y, right? So if we want to reference whatever was passed in here, this is what we use to reference it.
So I'm thinking if there's already, imagine this process P already has some name called Z in it. And then we happen to pass in the same Z. This isn't a fully formed question, actually. Maybe this is something I should think about first.
Okay, yeah. Yeah, I think if you think about sort of what names are sort of defined in your context and what you would, what sort of program you would want to have that would want to reference this thing before it's passed in. Yeah, I can't think of an example program where that.
Yeah, that sounds good. I'll kick that around a little bit.
Cool. Okay, so the reductions can apply in a couple of situations. Reductions can apply under composition. So if P is able to reduce to P prime, if you are running P in parallel with something else, that shouldn't prevent it from reducing. Under restriction, so if P is able to reduce and you put some sort of, you bind some sort of name in P, it should still be able to reduce. And those are the only places. So there's a couple places where reductions do not apply. So within a single summand. So if you remember the summand, what that meant was, the one summand results in a normal process. And in a normal process, you can be listening on many names, and you can be trying to listen on many names, you can be trying to send on many names, but only one of those will execute. So in this process construction, even though we're listening on X and receiving on X, we're doing that in the context of this one summand, which means only one of these things will happen. So this does not reduce. Another one is beneath replication. So, a process P, if it can reduce, if you have bang P itself does not reduce. And this is sort of, we can still get reductions of P in our process because we have this equivalence relationship that bang P is equivalent to P running in parallel with bang P. And so we've pulled out this process that can reduce. So if P has reductions, we have sort of infinitely many available running processes that are not reduced and infinitely many available that are in the reduced form. And then in this paper, also in different versions of the pi calculus, a reduction is allowed underneath a prefix, but in this paper it's not. So if you've taken any sort of amount of any process and you've prefixed it to have it wait for either input or wait to send output, whatever this prefix process does not reduce, even if it has sort of available reductions. So yeah, you can think of prefixing as freezing an atomic process. So what questions do you have about reductions? All right, I guess the next thing to note is that structurally congruent terms have the same reduction. So we defined our equivalences, our structural equivalences before, and we want a rule to say that sort of if Q is structurally equivalent to P and P reduces to P prime, and we have to define Q prime, which is the structurally equivalent to this reduction of P prime, because a process can have many different reductions. But if we have these things, we also know that Q reduces to Q prime.
So an example of a process that has many reductions, is that like the one Glenn did where there were two different ways the communication could have happened?
Yeah, exactly.
So that's why the top right P prime is, how were you saying it? Congruent to Q prime?
Yeah, structurally congruent.
Structurally congruent. Okay, got it.
Yep. That's why that's needed. So that's sort of just a yeah. I mean,
good.
you could also say here that Q reduces to P prime. But it doesn't. Yeah, it doesn't necessarily have to reduce to P prime, right? So it can.
Yeah.
Reduce. Yeah. Okay, so I think that's where we'll stop today. I did have some slides for the derived forms, which if you all wanted to stay on longer, we could go through, or we could just save that for next week. But also, I just wanted to give a shout out to Joshi for helping me figure out how to make these slides. We have a GitHub, this RChain Collaborative Learning GitHub, and this whole slideshow was just created using Markdown with some LaTeX in it, and it just spits out these awesome slides. So that was great. And then is there just some explorations that you could do to sort of explore this material further? There's a bunch of exercises in the text that could be done. We have full information needed. We have the three things that we need for a programming language: the grammar, the structural equivalences, and the reductions. So we have enough that we can create a K framework or an Idris definition. Dan has started on an Idris definition. Rinke had an idea that we could have, say, a process out loud example. So making sure that we sort of have the vocabulary for par or run concurrently with sort of written down somewhere. And we could do more free name, bound name examples, implement more examples in the JSON Pi interpreter. And then I want to sort of open it up to you all to decide sort of where we head next. Now that we have, I think, a pretty good base for the Pi calculus, we could try to implement it in language definitional tools, and we could have further sessions sort of go into introductions to Idris or Kay or Kak or Isabel. We could continue with Milner's tutorial text and learn how to prove different properties of programs, and find the different equivalence relationships that we have aside from just structural congruence. We could sort of jump from here to an extension of the row calculus, and then kind of from there we could go into the Ladle paper, and we'd probably need a stronger like mathematics or type theory introduction as well for that. We could do programming in Erlang. We could go over some RChain implementation details, the RSpace, system level contracts, that sort of stuff. We could go over the Lambda calculus, or sort of really any other ideas that you might have. So I have a feedback form, a link to a feedback form. I will paste that in the chat right now. To everyone who's provided me feedback in the past for the last session, thanks. That's been super helpful. Let me try to get the chat. And yeah, any feedback provided in the future will sort of determine the direction we're going. So that's all I have for today. I'll open it up to you all to sort of discuss this, or what other hopes you have for this collaborative learning session.
I was thinking it might be nice if we had some kind of forum for interactions like in between the sessions. So for example, like I was working on the exercises and the reading. I feel pretty confident about one, but not at all confident about the other. And I was like, if this were a class at school, I would be like, meeting up with my classmates or whatever, trying to figure it out. I wondered if anybody had thoughts about that.
I'd be happy to meet up and do that if that's something that you wanted to organize. Yeah, I think there's the Google group, which you could use to send emails to everyone.
Yeah, I got it. Okay, cool.
Any thoughts on the where to head next?
Yes. I wanted to say what Dan has implemented something in Idris. Could you show that? And what is
Can you hear me?
doing already?
Hello?
Yeah, we can kind
Hi,
of hear you.
we can hear you.
Nice, thanks. Very loud here. So the way you introduce the points, it sounds like Milner's tutorial text would be nice, actually. My state of point. And then would be better to go to row calculus. That's my opinion. Do not know what you think, guys.
Okay, so yeah, sure. We can continue with the tutorial text. Yeah, and you said you wanted to see the Idris stuff. Oh, I should have made that a link. Oh, I did. So here's some of the work that he's done here. And I guess, yeah, we could go over this sort of in more detail.
That would be nice.
In a following week.
Yes. To get some kind of intuition on what kind of statements we can put here and what kind of how proof comes in there. I'm very interested to see what we can actually prove then and how this works out.
Okay, cool. Yeah, I can do that. That's going to take some exploration on my part. So if someone else also wants to help with the preparation of this material, if you could at me, that'd be great. But yeah, I'll definitely poke at this for next week. And then I'll also poke at continuing with the tutorial. I think a cool thing about this Idris definition is, so Dan's gone up to defining free and bound names of processes. So this could serve as a great review for the free and bound name stuff, the stuff that we've reviewed, that we went over this week for next week.
Yeah, I think that would be really helpful.
Okay, great. Yeah, if there's no other comments, we're about like 5 minutes over. Sorry about that. But yeah, I'm glad that you're all here, and that you're pushing me to sort of write some stuff down, prepare materials, and learn a bit better. So this has been great.
Yeah, thanks for doing all the presenting and preparation for this, Jake. It's really helpful.
Yeah, definitely. Thanks a lot.
Yeah, awesome.
Sure.
Well, oh, you're breaking up. Maybe you want to type in the chat, Phoenix. Ah, yeah, you're welcome. Okay, have a good week, everyone. See you later.
See you later.
Bye.